All right. So let me run through the answers here. Number one, they've got 35. Number two is 42. Number three, they have a fraction in here. 158 over 85. Is that what you got? I guess your calculators would give you a fraction too, wouldn't it? 47 over 60 for number four. Number five is 4C. Number six, they have 55,991 divided by 9,240. 6.0 something, I think, is correct. Number seven is 238, and number eight is 14. Okay? So, on our next quiz, there will be some sigmas, and on today's homework, it's in the book, but there's, some of these just simple expansion type sigmas. Now, today's main focus actually is this section right in here, where we're going to write out some sums, and we're going to write out these specific sums like this, left sums, right sums, midpoint sums. Okay, we're going to write them out, height times width, height times width, height times width, kind of like we did yesterday when we developed that definition of the integral. We're going to write these out, and then we're going to turn that into a sigma. So we're going to start with an integral, write out some rectangle sums for that integral, and then turn it into a sigma. That's our main objective today. So they'll look like this. So on this one, it was sigma 1 over 3i. Goes from 1 to 9. Number 11, basically 11 just was this, except instead of this 1 up here, you had an I, right? And the I went from 1 to 8, right? I mean, you just repeat basically what this is, except there's an I up there. 13, now it's a little harder when they only do the first term and the last term, but everything is the same here except this top numerator. So it'd be I, and I would go from 1 to 6, right? And this 1, 6 stays the same, but there'd be an I there. Okay, 15, what's that? I would leave it in there. Yeah. It doesn't matter, though. It doesn't matter. The only reason I like leaving it there is because of this. It's kind of like this. On this, we could pull that delta x out because it's in every term, but I like height times width, height times width, height times width. That's the main thing. All right, and then 15. So now this one is a little trickier. The 2's here turn into 2 n's. So it's 2i here and here, and I goes 1 to n. Yeah, I goes 1 to n. So what would be the second term here? This would be if there was another one here, this would be a 4, right? And this would be a 4, but this one would just stay a 2, right? So it's like 2, 4, 6, 8, and then it's 2 times whatever the last one is, and that's 2n. So it's a little harder to see the pattern if all you have is the first and the last, but they just didn't have room, I guess. Same thing on this one. Everything's the same in these terms except this numerator right here starts as a 3, ends up as a 3n. So that'd be 3, 6, 9, and then 3n. So it'd be 3i in your sigma. Okay, so just seeing the patterns, that's what that's about. Then we had those properties. Now 21, they did something a little bit interesting. If you looked in the answer book, which you may not have done, but a few people were in this morning and we were looking at that, and they did something kind of interesting, and it's worth pointing out. On number 21, now 19, the answer is 420. On 21, it's 2,470. And on 23, it's 1,015 over n cubed. The n cubed you would just leave. Yeah, now that's a little confusing. You don't put the 15 in for the n here. So it's a little confusing because our formulas had n's in them. But that's not the same n as this n here. Does that make sense? I'm not sure. Well, it's kind of related to 21. I want to talk about 21 here real quick, though. And to be honest, this will be on the next quiz, probably where we use the formulas. But if we look at this one, the way I talked about doing it was FOIL this out. So you get this. So then split it. So you get sigma I squared minus 2 sigma I plus sigma 1. Now, according to the formula, sigma I squared, and this goes 1 to 20. So I squared would be n times n plus 1 times 2n plus 1, is that right? All over 6. And then minus 2 times, and then sigma I was n times n plus 1 divided by 2. And then sigma 1 would be 1 times 20, which would be plus. And then plus 20, right? I think that's it. Now that should come out 2,407. If you look up in the back of the book, they took this sigma and they rewrote it as I equals 1 to 19. I squared. Why would those two be the same? Well, right. But it's not really because of that. I mean, 20 minus 1 is 19, I agree. So the last term would be 19 squared. But how can you go from, this has 20 terms in it, and this only has 19 terms? Because the first one is 0. If you expand this sum out, you put a 1 in for I, you get 0 squared, plus then put a 2 in, you get 1 squared, all the way to 20, you get 19 squared. Well, geez, who cares about the 0? That doesn't add anything to it. So really what this is just 1 to 19 I squared. Now, I wouldn't expect you to notice that, but if you do it, then the I squared formula is n times n plus 1 times 2n plus 1 all over 6. I think if you multiply that out, you get the same thing as this. It's just simpler. But so I didn't expect you to see that. But what I do want you to notice is that sigmas are not unique. Any sigma that represents a sum, or let me say, any sum can have an infinite number of sigmas that could generate it. For example, I could take this same one here, and I could have went I equals 2 to 21, and then I minus 2 quantity squared. Wouldn't that give me the same sum? And then I could just keep doing that. I could go 3 to 22 and do I minus 3. I mean, so you could start the I anywhere and change your formula and generate that same sum over and over and over again. Now, what that points out to us is that any sigma we have, if we want to, we could write it starting at 1, which I think most of the time is what we want to do. The only exception to that, and you're going to see that today, is if we start I at 0. That can be useful in left rectangles, which is something we'll see here in a little bit. All right, so anyway, that's enough on that, but that's using those sum formulas. Okay, now, on this section, this was just n goes to infinity. This will probably not be on our next quiz. We just needed that when we were doing kind of the long version of doing infinite rectangles. So I don't anticipate that being on the next quiz. But it was just high powers dominant. So here, these wouldn't matter. These powers here, you'd have n cubes that cancel. You'd get 8 over 3. Here, when you FOIL this all out here, you'd have n to the 4th plus some other stuff that wouldn't matter. The n to the 4th would cancel. You get 81 over 4. On this one, distribute that, you get n squared plus some stuff that won't matter. N squareds cancel, 18 divided by 2 is 9. Okay, so that's n goes to infinity. Then this last section was kind of the summation, or the culmination of what we did yesterday is take what you did down here with the sum formulas. So this is kind of like number 23. So you can expand this out, whatever, then let n go to infinity. Okay, use the sum formulas, and then do what you did up there, high powers dominate, and you get those answers. I don't want to spend much time on that because, I mean, it was important, and I wanted you to be able to go through it with what we did to see that infinite rectangles really do give you the exact area, and we can show it mathematically. But again, not something I'm probably going to make you do. I'm more interested that we can take an integral area, write out the rectangles, and represent the sigma. And that's what I want to focus on today. Okay? So let's do that. So, we talked about Riemann sums, which is adding up rectangle areas. We talked about left, right, midpoint. That's what we want to focus on today. Maybe real quickly before we get into the next problem, I want you to look at this table right here. Now, this is in your book on page 355. Okay, but I'll just put this up here. And let's say this was a function f, And let's say I wanted you to do the integral from 2 to 5, and I wanted you to represent that integral, because let's face it, we don't have a formula, so we can't do fundamental theorem part 2. There's no antiderivative we can do. So we're going to approximate this integral using 3 left rectangles. Take just a minute in your notes, on your homework, wherever, I don't care, to write down what the answer would be with this information, 3 left rectangles. Draw a picture if it helps. If you don't need a picture, that's fine too. This is kind of like what we did yesterday in that problem with the 2012 free response question with the temperature of the water. Okay, what do you got? Shout out all at once. You don't got it yet? Oh, you did it wrong? Oh, you just copied it down? Oh, you copied it down. Oh, that's good. Okay. I didn't think you... That's fine. Okay. Don't shout it out yet then. All right, now what do you got? Shout it out. 0.85. 0.85 is correct. Now, why is that? Well, maybe if you draw a picture, right, one thing to do would be to just plot those points. And they all just keep getting bigger, right? And if we want to go from 2 to 5, of course, one of the things we said, the first thing you got to do is figure out what? The delta x, the width, right? So you're going from 5 to 2, so that's a width of 3. You're going to do 3 subintervals, so they're each 1 y, okay, which is good because our table goes by 1. But if I plotted all of these, the first left, and that's the key, when we do a left, we use the first left edge, which is right at 2. That's where our interval's starting. So we go up to there and go across. So that rectangle would have a height of 0.21. And the next one, 0.28. And the next one, 0.36. And we would not use the 0.44. The 5, where we end, that's the right edge. It'd look like this, f of 2, f of 3, f of 4, each times 1. So when I say write out an L3, I'm talking about this back here, right? F of x of 0, f of x of 1, right? All the way till 1 short of the right edge. If you're doing a right, you start at the first right edge, right? 1 width over from your left edge, and then all the way to the far right end of the interval. And then, of course, midpoints we're going to do in a second. So anyway, it'd just be 0.21 times 1, 0.28 times 1, 0.36 times 1, 0.85. Okay, let's do this again, except let's change this a little bit. Let's do the integral do the integral from 1 to 5, and let's do it with an M2 calculation. M2 means 2 midpoint rectangles. 2 midpoint rectangles. What do you got? Anything yet? 1.14. Could we have done an M4? What do you mean it wouldn't have been? Because we don't know what the, in other words, if we go from 1 to 5, that's a width of 4. And if we want to do 4 midpoint rectangles, they got to each be 1 wide, right? And we have to do the middle of those. So we would need to know in the middle of 1 to 2. We need to know what the y value was at 1.5, and we don't. Yeah, well, that'd be a guess, basically. I mean, it'd be, you kind of guess what's happening. This goes up 0.7 and 0.7 and then 0.8 and then 0.8 and then 0.10. But, that would show you, and you can't do that. And to be honest, we would never ask you that. So they're not going to try to trick you into that. But there's a reason. So if you had a table like this, they might ask you for an L4 or an R4, but they wouldn't ask you for an M4. They'd ask you for an M2, right? Because we do that. So in my picture here, so if the picture helps, and what I was trying to show you with this is, if the picture helps you to visualize your rectangles, to write them out, then by all means do it. Absolutely do it. And so I did that. I said, okay, I'm going to get my width, right? Delta x, we got to get that width right away. So 5 minus 1 is 4. We're doing 2 of them. 4 divided by 2 is 2, so they're 2 wide. So I did a dot at 1, a dot at 3, and a dot at 5. So the width is 2. The midpoint's halfway in between. So we need the y value at 2 and the y value at 4. Now, you could have written that out without a picture. You could have said, okay, I'm going to go from 1 to 5. I need 2 rectangles, so they're going to be 2 wide. So one will be this wide, one will be this wide, and I need the midpoint. So it's that point and it's that point. And so I could have just written it, without the picture. But if the picture helps, by all means, use it. Okay? All right. So that's just a little bit on that. We could do a trapezoid. We could do a right with that data as well. All right. Let's move on to this. This is our objective today. We want to take an integral, and we want to write the sigma version of some approximations. Okay? So what we want to do is what we talked about yesterday, which is be able to write out left rectangles, right rectangles, or midpoint rectangles. But then once we've written them out, we want to then write them as sigmas. Well, and as we learned yesterday, is if we see a pattern when we write out a sum, the sigma should be easy to write. And I hope that's the case here. So let's start with this. So I think a good place to start is to draw a picture. Don't have to, but I don't think it's all bad. So 2 would be about here, 5 would be about here. So we're talking about this area here that we're finding. Now, I often, if this function is some function I don't even know what it looks like, I don't even care in my picture. All I really need in my picture is my x-axis. Because I need to know where I'm starting, I need to know where I'm ending, I might need to know the widths, that kind of stuff. So I want to do an R10, right? So I'm going to start it to write a sigma. I think it's best to write it out, expand it out, and then see the pattern, write the sigma. So I want 10 right rectangles. So first job is to find the width. 5 minus 2 divided by 10, 3/10. So delta x is 3/10. Okay, so that means from 2, I'm going to go over 3/10. And how should I write that? Yeah, we could write it 2 and 3/10, or we could write it 23/10. I'm kind of partial to improper fractions, so I would probably write this 23/10, 20/10, probably write this 50/10. Now you could write it as a mixed. You could write it as 2 and 3/10. You could even do decimals if you want, 2.3. I think decimals are harder than fractions when it comes to these patterns, so I usually do this. But I'll show you a little bit of the mixed number 2 and see what you think. So I have 23/10, 26/10, and so forth, right? So you can see I don't really care about this picture, but the x-axis is helpful for me to just see my different points. All right, what would I write? And let's use F notation here. So my first right rectangle would go up at 23/10 and then over, and that would be my first rectangle. So the height would be F of 23/10 times the width of 3/10. Correct? That's going to give me my first rectangle area. Now, if it helps to draw the picture of the actual rectangle, then do that. The function value at 23/10 is the right edge. That will give me the height of that rectangle times the width of 3/10. Okay, plus what would be the next one? 26/10 times 3/10. And I don't think we need any more. 29, 32, on and on. But I think we should do the last one. And what's the last one? 50/10 times 3/10. So that's going to give me 10 rectangle areas, height times width, height times width, height times width, right? 10 rectangle areas. I add those up. That will give me an approximation for this. Now, if you got your calculators handy, we're going to type that sigma in. Oh, did anybody type this integral in, by the way? Why don't you do that real quick, and let's see what this area actually is. Let's see the exact area of this thing. I'm just curious. We couldn't do a fundamental theorem part 2 unless you've memorized natural log's antiderivative. It has one, but it would take integration by parts to get it. I think we did it one day. Anybody getting an answer for that? Okay, so that exact area is 3.661. All right, so when we get done down here, we're going to type this sigma in and see what we get. All right, so my sigma is going to be, I is going to go from what? 1 to 10. Now let me make a comment about this right now. There is no connection between these numbers here and these numbers here, right? These numbers tell me how many rectangles I have. These numbers tell me the width of my interval, right? So understand that these are not connected to those. All right, anyway, 1 to 10. And then F would be here, the parentheses would be here, 3/10 is in every one of them, right? There's a 10 on the bottom. Remember how we talked about that yesterday? So the only thing we have to generate is the 23, the 26, all the way up to 50. 20 plus 3i. Now, if you're having trouble seeing that that's 20 plus 3i, here's my suggestion to you. Look at that number and see that it's adding 3 every time. 23, 26, 29. You're adding 3 every time. What's that mean? Well, repeated addition, by definition, is multiplication. Repeated addition is multiplication. So, when you're repeatedly adding 3, what you're doing is multiplying by 3. So when you see repeated addition of 3, you think 3i. And then you just make an adjustment. So 3i, that would give me 3, 6, 10, or excuse me, 3, 6, 9. Well, you can see that's just being added on to 20. So that's where you get 20 plus 3i. Now, sometimes you will see books write that as f of 2 plus 3i over 10 like that and do it as a mixed number. So they think of it as 2 and 3/10, 2 and 6/10, and all the way out to 2 and 30/10, which would be 5. Okay? I'd rather do it as improper, but you can do it as a mix as well. All right. So there's our sigma. And then the last step, yesterday we said let's take it out of F notation and put it into our function. So we take this stuff here and we plug that in there for the x. So ln of 20 plus 3i over 10 times 3/10. Now, you want to put that in the calculator, somebody? See what we get? Because while you're doing that, it would, even to do 10 rectangle areas, to do 10 individual rectangle areas by plugging them into natural log, you know, you could go 23/10, plug it into ln, times it by 3/10. Then you can take 26/10, plug it into ln, times by 3/10. And you do that for 10 rectangles. It wouldn't take too long. But if you want to do 100, 1,000, it would take forever. So writing sigma notation is a good way to do this. What do you get? 3.796. So a little bit too much, which makes sense, that the rights are a little bit over. But it's not a bad approximation. Now here's where the real power in the sigma notation is right now. What if I changed my mind and said, I want to do R of 100? I would do 100. Well, what would change to 100?
All the time.
This would change to 100. That would change to 100. That would change to 100. And you're missing one thing. That would change to 200, right? Because this would be 200 hundredths, and our width would be 3 100ths. So our first width over would be 203 100ths, 206 100ths. So this would be 200 plus 3i. Okay, put that in as your sigma. Now, just change those numbers. Yeah, so that's getting really close, isn't it? Getting really close now with 100. So the power of the sigma notation is we can represent our sum, and then we can do 100, we can do 1,000, and we can just change it and tweak it just a little bit. Okay, now that's very much what we did yesterday, right? We did 4, we did 100, we did infinite, okay? Today I'm not as concerned with infinite. Now infinite, of course, would give us the exact area, right? But these are just approximations. But yesterday we did rights, and those are pretty easy to draw. So what if I wanted to do a left for this same thing? Yeah, let me write out a little bit of it, but you're going to see. Let me put my 2 and my 5. Okay, this was 20 tenths. This was 50 tenths. This first one here was 23 tenths, right? Had my curve, da-da-da. But this time my first one is going to be, okay, so let me write this. So L10, so it'd be F of 20 tenths times 3 tenths. Okay, everybody with me? So this time, instead of starting at 23 tenths and going back, and that's my first rectangle. Now, when I start at the left, it's going to be at 20 tenths. The next one will be at 23 tenths. And my last one is at 47 tenths, which is 1 width short of the end. Left's always in 1 width short of the end. That'd be 3 tenths short of here, 47 tenths. Now, when I go to do my sigma, now, yes, one thought would be to do this, right? And the F is the same, and the 10 down here, and the 3 tenths is the same. And we're still going up by 3, so you still think of 3i, but the first one you want is 20. So what Kelsey's saying is, how about just do 17 plus 3i? And that would be okay. That would do it. Put a 1 in, put a 2 in, you would get those. But what do you say?
You go from 0 to I to 0 and 9 on top.
This is why I mentioned this earlier. It turns out that we can use the same exact formula we did for rights just change that to 0 to 9. Doesn't that do it? And I don't care. You can adjust it and start I at 1, but here's what's going to happen. Next week, today we're doing integrals, changing them into sigmas that represent the sum for our approximations. On Monday, we're going to do sigmas and turn them into the integrals. We're going to go backwards. Well, what's going to happen is whenever you have a left, they're going to start it at 0. So that's going to be like this big hint to you. Oh, it started at 0. I'll bet this is a left rectangle situation. If it starts at 1, you're probably going to say a right rectangle situation, right? So that's pretty cool. So in your homework, you're going to have some problems where they're going to give you an integral. They're going to tell you to do 10 right rectangles. Then in the next problem, they're going to say, do the same problem with 10 left rectangles. Well, that'll be easy. You'll do all this work and you'll set up this integral, and then all you got to do is change that to 0 to 9, and you'll have lefts automatically, right? So that's a nice adjustment you can make with your sigma notation to take care of that. Because the only difference between the right and the left is the right starts 1 over farther than the left does. Okay? So you just start your index 1 farther over, and that's the difference between right and left. All right, so let's do a midpoint. This one does get a little bit tricky and messy. And no, okay, let me write it. So we got this same function again, going from 2 to 5, and that's log x. All right. This would be 20 tenths. This would be 50 tenths. Okay. So our width is still 3 tenths. The delta x is still 3 tenths. And we want to do 10 midpoints. So where is my first midpoint going to be? 21.5 tenths, which we really probably shouldn't write. So that would actually be 43/20. Now this is going to be your giveaway. If you want to take half of a fraction, you double the bottom number. So with midpoint, now somebody in the other class came up with their sigma. They said, well, if lefts start at 0 to 9 and rights go from 1 to 10, how about midpoints start at half and go to 9.5? Well, then Jared Nightingale typed it in the calculator. I said, no, you can't do that. That doesn't work for sigmas. And he typed in the calculator. It worked. Oh, okay. I didn't know that. Which would be easy to program. I could understand why it would work. And I always kind of wondered why they wouldn't let you do that. Unfortunately, when we look at the AP test and the problems in the book and so forth, they don't let you do that. So we're not going to do that either. I think the tradition has been with sigmas, they have to be whole numbers. So we have to adjust our formula. We can't adjust our index to take care of it. Too bad, because it would be a simple adjustment. All right? So, but here's the adjustment we will make. We'll just double these to make that 40/20 and 100/20. Now, to be honest, I'm still going to call my width 3 tenths. The reason for that is that's going to give us a hint that midpoint is what we're doing, because that's the way they tend to do it in the book problem. So I'm going to do that too. So I'm not going to call this 6/20. But kind of in the back of my head, I'm thinking to myself, okay, my width is 3 tenths, but that's also the same as 6/20. So my width is 6/20. Now remember, when you do a midpoint, you've got this dot here, which would be at 20, or no, that'd be at what, 46/20. But halfway is what we want, which is 43/20, which is what you guys said. So this is going to be 43/20 right here. Now, next week, I'm kind of looking ahead a little bit to next week. When you see one of these next week, where the width is this and the inside there is that, you're going to think, hey, that's midpoint, right? So if you see a sigma that starts at 0, that's going to tip you off it must be a left. If you see a sigma that starts at 1 and these match, notice how that's 10 and 10, 10 and 10, 10 and 10. You say that's a right. And then when you see a 20 and a 10 like this, you're like, oh, that's a midpoint. Okay, so those are kind of your tip-offs of what's going on. All right, so now this is always kind of tricky. What's the next one? It's got to be 49/20. That's right. because you have to add one width. Remember, when you go from the middle of this to the middle of the next one, that's a full width over, which is 3/10 or 6/20. So that next one's going to be 49/20. And the last one is what?
94. 94.
Yeah. This would be 94, but the midpoint, right, is half a width. Think of that. The last midpoint is half a width from the right edge, isn't it? So half a width would be 3/20 away from there. So it would be 97/20. Okay? Now, if I'm going to write that sigma, I'm going to still go 1 to 10 for midpoints. I still have 10 of them, right? So I got my F. I got this. I got the 20 on the bottom. I got the 3/10 here. And then what would be up here? Now what's it going up by though? It's going up by 6. So that makes us think 6i.
43.
Like put it as 43/20 plus 3i. It would start at
Wouldn't it be like
37.
37?
No, and then you do the like.
Oh, and then and start I at 0?
Yeah.
Yeah, you could adjust it, and those would be okay. If she did 0 to 9, she could go 43/20 plus 3i over 10 or 6i over 20, right? Those would all be okay. Or we could go 37 plus 6i. That would do it, right? Or you could go 37/20 plus 6i over 20. You're right, because remember what we did with antiderivatives, how we split apart these fractions? We could do that. It would make it more of a mixed number, but that's okay. Yes, so you definitely could do that. You definitely could do that. You could think of this as your first midpoint is 2 and 3/20, and your next midpoint is 2 and 9/20, right? Isn't that the next one? And so you could write these as 2 plus 3. I mean, there'd be all kinds of ways to write it. Remember we said that the formulas are not unique. So that's fine. I don't care. Now, typically, we start at 1 for all of them except for lefts. But you wouldn't have to, right? You wouldn't have to. So it's more about what it would expand out and what it would represent. And if I really wanted to try to quiz you on this, really test you on all of that, then I'd give you a bunch of different ones. It started at different places and have you expand them and then be able to think, is it a left, is it a right? At some point, I don't think we need to get that deep into it, to be honest with you. But, all right, and then the last step would be to take it out of our F notation into the LN notation. You can type it in and see what you get. But this is the main goal on the homework today. There's going to be a few just simple sigma practice again, a few with the summation formulas, and then there's going to be some where they say, okay, here's a function, do R10, write a sigma for R10. And then actually there's parts A, B, C, and D. It'll say R10 and then do R20 and then do R50. Well, once you've written one, you can adjust the other one pretty easily. Okay, and then the next problem will say, now do the same thing with that problem except do lefts. Well, you can adjust that pretty easily too. So it looks like a lot of problems, but yet you're not going to be expanding a bunch of them out. A lot of them you'll be adjusting once you've already got one done. Okay, so that's our main goal. So our main objective here is starting with an integral and writing its equivalent sigma. Next Monday, we'll go the reverse. We'll start with the sigma and we'll say what integral was it that generated that, kind of go in reverse. Okay, so here's the homework in the book. 1 through 4, just a few simple sigma expansions. 5 through 11 odd is some summation formula ones. Some of those I don't think you need the formulas. I think you can just expand them. They're small enough. And then these are the ones I was talking about that have multiple parts. I think 13 has you do a bunch of rights. 14 has you do lefts for that same thing. I think 19 does it again, some rights, then some lefts. And then 23 is some midpoints. Do some midpoints. Okay? So it's just like what we just went through with that problem. All right, got the rest of the time. When do we get out of here?
54.
Oh my God. Should make this assignment longer.
No.
All right. Okay.
Basketball celebration.
Yeah.
Basketball.
It.
I gotta be extra nice.
Yeah, mom didn't.
I'll tell you what,
Mom didn't
it-
give her kids homework.
Yeah.
Wow.
Last
Go to the
night.
game.
Yeah.
Oh.
Maybe you should just take this aside.
Well, you notice I didn't go around and check your homework. Did you do it?
No.
Yeah. See. Even did it.
Take it back.